Chapter 6.2 is on inverse functions. Before we can proceed with the definition of inverse function, we first have to define what is a one-to-one function. So a one-to-one function, and the reason we need to do this is because inverse functions are comprised of what of one-to-one function. So a one-to-one function has or is a function in which every element of the range of the function corresponds to exactly one element in the domain. Another way of saying this is that it has exactly one x value for every single y value. In other words, the values are unique. We're going to look mostly at how to determine one-to-one functions from a graph. To determine from a graph if a function is one to one, use a horizontal line test. Horizontal line test. If a horizontal line can intersect the graph more than once, then the graph slash function is not one to one. This is distinctly different from the definition of a function, where a function used a vertical line test, and if the vertical line crossed the graph or intersect the graph more than once, then we know that it's not a function. But this is uniquely different from that. So we're going to look at a few examples of this. Let's sketch a few graphs here. And let's go ahead and take a simple, say, graph like this first. And then here we're going to consider a graph perhaps like this. And if we performed a horizontal line test anywhere on this graph, we can see that it only intersects once. So this passes the definition, and it is 1, 2, 1. Now, if we did the same on this graph, we can see that it intersects more than once, so not 1, 2, 1. Now, let's consider, say, a simple square graph, quadratic graph. Here, this graph fails the horizontal lines test. It intersects twice. Let's say this is the graph of f of x equal to x squared. Fails the definition, so not 1 to 1. Because the horizontal line intersects more than once. Now, if we were to restrict this graph to, say, all values, and we say for x greater than or equal to 0, in other words, we're only taking a portion of the graph, like that, for all values from 0 to infinity, that restriction would make this particular function with that restriction would make this graph 1 to 1, because now a horizontal line would only intersect it once. So this is 1, 2, 1. So now we can proceed to define the inverse function. Now that we kind of have an understanding what one-to-one functions are. Inverse functions, the definition and the properties are multiple and varied, so we're going to consider several of them. All inverse functions are 1 to 1. See why we did 1 to 1 functions? Because we needed to know what a 1 to 1 function is. The inverse of a function f of x is written as f inverse x. I'm making this as simple as possible. The domain of f of x is the range of its inverse. And the range of the original function f of x is the domain of the inverse. All right, now a couple of other properties. If f of x and g of x are inverse functions, comma, then, I think I have that comma in the wrong place, then, and we're going back to what we learned about composition functions now. F composed of g, which is the f function substituted with the g function, must equal to x, and g of f, g substituted with the f function must equal to x. These conditions must be met in order for the functions to be considered inverses. And finally, f of x and its inverse are a reflection on the line y is equal to x. This is a nice little property that you can see when you actually graph the function. If I can just give you a quick illustration of it. So y and x, and we called it if we put a line through the origin y equal to x, the straight line through the origin with x equal to 1, y equal to 1, and so on. The graph, if we illustrate the graph of one function and its inverse here, and we can do this by perhaps sketching a simple graph and showing how the inverse works. Let's see. So if I had a graph perhaps that looks like this, and call that f of x, the inverse would be a graph coming this way and nicely reflected on the line y is equal to x. And you can see every single domain value on this graph. Let's say that domain, let's say the coordinates at that point are 1 and 2. Then this graph would have 2 and 1 in its domain. Sorry, as a point, the domain and range values would be flipped around. We actually don't need the rest of this graph. We can just go ahead and remove it and see what we're talking about here. Okay. All right. Now, examples on finding the inverse. Find the inverse of the given one to one function and state its domain and range. That given function is f of x is equal to a set of numbers, say -10 and 0, -9, -3, -8 and 12, -7 and 8, and -6 and -4. Okay, so we're told that the function is 1 to 1. In other words, it passes the definition of has exactly one x value for every single y value. Now, the inverse function would simply be every single point, for every single point we interchange the domain and range values. The domain, of course, would be the list of all the x values without repeat, and the range would be the list of all y values without repeat. Notice that for the original function, notice for the original function, the domain was -10, -9, -8. I think I'm missing a number here. -10, -9, -8, -7, and -6. Yeah. And the range would be 0, -3, 12, minus 7, and negative 6. So you can see what's happening here. The domain and range values are completely flipped around. I think I have something incorrect here. The domain 0, I'm just checking back here. The domain is 0, negative 3, 12. Ah, right here. Right here. Yep. I didn't reverse this one. Oh, so this is 8. You guys would have been calling me out with that mistake. Okay. So, um, what? If I noticed that because when I went to write the range of this function, that 8 is missing. Now you can see what's happening here. These are the domain and ranges interchanged. Okay, the numbers should match, which is why I picked up that little mistake that I made just now. All right, now to determine if functions are inverses, given f of x is equal to negative 2x plus 9 and g of x is equal to negative half x minus 9, find f composed of g and g composed of f, and determine if f of x and g of x are inverses. So we said in our definition that the composed functions, must equal to x in order for them to be considered inverses. So let's go ahead and give this a shot here. This is f composed of g, which is f substituted with gx, is the f function substituted with the g function. If you want to make your life a little easier, you can probably distribute this out. This is negative half x plus 9 over 2. That would make it easier when you substitute it. So this is negative 2 plus 9. And in that space, we're going to write the entire g function, which is negative half x plus 9 over 2. Distributing negative 2 times negative half is 1. And that leaves an x there. And negative 2 times positive 9 over 2 gives negative 9 plus 9, which is equal to x. Now we can't stop here. We have to do the second part, which is G composed of F. In other words, the G function substituted with the F function. And in this case, this is negative 1/2 plus 9 over 2. And into this space, we're going to substitute the entire F function, which is negative 2x plus 9. So this is equal to distributing negative half. We have x minus 9 over 2 plus 9 over 2, which is equal to x. So part C, since F composed of G is equal to G composed of F, they're both equal to x, F of x and G of x are inverses. I wanted to go ahead and graph this function and these two functions and show you what I'm seeing on my calculator. So I've got negative 2x plus 9, and my second function is negative half x plus 9 over 2. Now, because this window is a little distorted, you're not seeing the symmetry, so I'm going to do a zoom square number 5 to try to get a better picture of this, and then I'm going to put in the line y is equal to x. And now you can see the perfect symmetry of the line of the two graphs around y is equal to x. Let's go ahead and capture the screen and put it in our notes. Okay, just to get a good illustration of what the graph looks like. That line going through the middle is y is equal to x. This is the line with the negative slope. What's that equation? Negative 2x plus 9. And this is the line with the pause. I'm sorry, they both have a negative slope. So the intercept, pardon me, this is the line with, what's that equation? This is, yeah, negative half x plus 9 over 2. And this is the line of negative 2x plus 9 because the intercept is at 9. Okay. And you can see the symmetry about the line y is equal to x in the middle, how the graphs are beautifully reflected on that line. Do another example here. So f of x equals to x cubed minus 5, and g of x is equal to, say, the cube root of x plus 5. So f composed of gx is the f function cubed minus 5, and into this we tack the g function, which is x plus 5. And we know that the cube and the cube root go away to give x plus 5 minus 5, which is equal to x. The g substituted composed of the f function. So the g function is the cube root plus 5, and into this we write the complete f function. So this is the cube root of x cubed, which is equal to x. So yes, f of x and g of x are inverses, since f of x, f composed of gx is equal to g composed of f of x, both equal to x. Again, I want to take you back to the calculator here and show you what these graphs look like. So we're going to type in x cubed. Let's clear these two graphs out. We're going to keep y equal to x there. It's already in the square window. And we're going to go ahead and type in x cubed minus 5 cube root, so math cube root of x plus 5. And let's look at this graph. See the beautiful symmetry there? We're going to go ahead and capture this and put it into our notes. So here we have the graph of y is equal to x, and then next we have the cube root function shifted 5 places to the left, and the cube function shifted 5 places down. And illustratively, I want you to notice points on this. For example, 5 and 0 and 0 and 5 are on the same graph. Negative 5 and 0 and 0 and negative 5 are on the inverse graphs, to illustrate that the range and domain are flipped around. Okay, how to write the inverse of a 1-to-1 function. By the way, notice that all of the functions that we've dealt with so far for the two examples here are 1-to-1, okay? They're all 1-to-1 functions. 1-to-1, 1-to-1. All of these are 1-to-1 functions. I neglected to mention that, but they all pass the horizontal line test. Okay, now how to write the inverse of a 1-to-1 function? A couple of rules. One, replace f of x with y, interchange x and y, solve for y, then replace y with your function notation f inverse x. All right, so I'm going to do an example here of how we're doing this. We are going to find a couple of different things here. Okay, given f of x is equal to 8x minus 2, we can already establish this is 1-to-1. Okay, A, find the inverse function. So f of x is equal to 8x minus 2. That's step 1 says to replace f of x with y. Then interchange x and y. So in place of y, I'm going to put x, and in place of x, I'm going to put y. So x is equal to 8y minus 2. Next, we solve this for y. So we get 8y is equal to x plus 2. So y is equal to x plus 2 over 8. Then we tack in the function notation. Now, I want to show you how straightforward it is to sketch a graph of this, okay? If, let's call this part B. So if we wanted to graph the original function, say f of x is equal to 8x minus 2, I would quickly find 2 points. Say when x is equal to 0, by substitution, y is equal to negative 2. And when x is equal to 1, y is equal to 6. And plot those points, maybe take a few points in each direction. 1, 2, 3, 4, 5, 6. 1, 2, 3, 6. So plot 0 and -2 right here, 0 and -2, and then plot say 1 and 6, 1, 2, 3, 4, 5, 6 right there. And the not so fun part is trying to sketch a graph with this tool here. Let's see if this works. All right, this is may or may not work. Let's see. Okay, so there's my graph of f of x equals to 8x minus 2. Now, here's the really easy part of this. If we're graphing the inverse function, we don't need to calculate a set of new points and substitute it in here. All we need to do is take the two original points and reverse and interchange the x and y values and plot these 2 points instead. So this time we're going to plot, say, -2 and 0. And we're going to plot 6, 1, 2, 3, 4, 5, 6, and 1. Right there. And we're going to put a line through those points. So here we go with this line tool again. Okay, and this is the graph of f of x is equal to x plus 2 over 8. Right there. And you know that if we put a line through the middle, y is equal to x, you can see the symmetry of that. I'm also going to graph this with a calculator so you can see it, and put the graph into the notes here. So clear this out and we type in 8x minus 2. And then clear this out and we type in x plus 2 over 8. And this should match the graph that we sketched, shouldn't it? Yes, there it is. So we're going to go ahead and capture that and put it into our notes also, just to show that the graphs match here for us. You know, this is the graph of f inverse x, f of x, and y equal to x. A couple other things about these problems. You may be asked to find the domain. Since all of these are linear functions, the domain of the domain of the original function is negative to positive infinity. The range of the original function is also negative to positive infinity. So the domain of the inverse function is still negative to positive infinity, and the range of the inverse function is still negative to positive infinity. This is going to change ever so slightly if we consider an example, say a couple of examples where um, the domains were different. Um, uh, let's take an example here. I have, say, f of x is equal to x squared minus 10. And this is a square function, so it's specifying that x must be greater than or equal to 0. In other words, we're taking only a part of it. And I want to go ahead and start sketching that on the side so you can see what it looks like. So we're going to mark 10 right here, and we're going to mark 10 right here. This is negative 10, negative 10. This is, of course, y and x. And we know that this graph is when y is equal to 0, x is equal to 0, and then when x is equal to 0, it's probably going to pass through somewhere at 3 point something. So if we sketch this graph, it will look sort of like this, half of it. Okay. This is the square root of 10, that point, the square root of 10. When y is equal to 0, x is equal to positive square root of 10. This is the graph of f of x equal to x squared minus 10 for x greater than 0. So we're not taking plus or minus square root of 10, just square root of 10. So now we're going to go through the process of finding the inverse. So y is equal to x squared minus 10. Then interchange x and y, so x is equal to y squared minus 10. So y squared is equal to x minus 10. So y is equal to the square root of x minus 10. Just keep in mind here about the domain and range. The domain of the original function, keep writing B. The domain of the original function is all x such that x is greater than or equal to 0. And the range of f of x is equal to all y such that y is greater than or equal to negative 10. What this is telling us in effect is that the domain of the inverse function is x. We take the y, change it to x. Now x is greater than or equal to negative 10. And the range of the inverse function is y greater than or equal to 0. So this is our inverse function here. F inverse is equal to the square root of x minus 10. Okay, and it's kind of specifying that x can only be greater than or equal to negative 10. So we don't take plus or minus the square root of negative 10. So to plot this, all we would have to do is reverse the 2 points that we took. That will be the square root of 10, 3 point something, and we make a graph going this way. And this would be the graph of f inverse equals to the square root of x minus 10. Y is equal to x goes through the middle. This graph is probably a little more difficult to see if you were to graph it with the calculator, because the calculator is going to attempt to put in the full graph for x squared minus 10. So you would probably want to restrict the graph to between 2 points, and it's not going to come out exactly the way you want it to. So I wouldn't do this with the calculator. You can probably do it with the Desmos calculator and specify x greater than or equal to 0 and see what's happening. What I'm trying to say here is that if I went ahead and graphed this with the calculator, I would have, there's ways to do this, by the way. If you go on YouTube, you'll see a lot of videos on how to graph this, but for our purpose, it's not really necessary, so we're not going to look at graphing it. So this is the square root of x plus 10. Okay, so you can see it's attempting to put in this portion of the graph, the portion for x less than 0. So if you really want to see a good picture of this, you would probably have to restrict it to the first quadrant and fix the window by saying, x minimum is 0, and the y minimum is 0, and graphing it. And then getting a better picture of the graph with the calculator. Okay. All right. Now, I wanted to touch one final example for you here. And this is f of x is equal to x cubed minus 10. So this is the cube function down 10 places. And we're going to first find the inverse. So y is equal to x cubed minus 10. So x is equal to y cubed minus 10. So y cubed is equal to x minus 10. So y is equal to the cube root of x minus 10. So f inverse is the cube root of x minus 10. Things to notice: the domain of the original function is by the way, I didn't specify that this is 1-to-1, but yes, it is. They're both 1-to-1. The cube and the cube root function are both polynomials, so they're 1-to-1. So b of f of x is negative to positive infinity. The range of f of x is negative to positive infinity. Therefore, the domain of f inverse is negative to positive infinity, and the range of f inverse is negative to positive infinity. Remember that when you're writing this, please if you're using the set builder notation, to use Y. Or say X all real. So here we have the, in this case, we have the cube function down 10 places, and here we have the cube root function shifted right 10 places. So we're going to go ahead and put that in the calculator and get a nice picture of it. So first function is the cube root. Sorry, the cube function up 10 places, down 10 places. And our second function is the cube root function. Shifted, I'm sorry, did I have this reverse? Let's see. Down 10 places. Oops, there's a mistake right here. Did you guys see that? This should be X plus 10. Yeah, I know there was something wrong when I'm trying to graph it. Yeah, X plus 10. So shifted left, X plus 10. Ooh, that was not a good mistake. Zoom standard or zoom square to get a good picture of it. Okay, so I messed up the window, so I'm going to put this back in the standard viewing window first and then get the graph of zoom square. Zoom standard. And then get the graph of the zoom square. Okay, so capture this. Paste it. So here is our cube root function shifted 10 places to the left. And this is our cube function shifted 10 places down. And of course, this is the line y is equal to x.